Okay, welcome to Chapter 2, Section 7, Chemical Nomenclature. Here we are going to limit ourselves to ionic compounds and binary covalent compounds. We won't be talking about alloys or semiconductors or organic compounds. Organic compounds, for me, comes in second semester, where we start diving into those. Okay, first up, ionic compounds. Now, if you want to leave it at its simplest, you just use the name of the cation, then the name of the anion, and you're done. Of course, that is not as simple as I might make it sound, because there are different kinds of cations and there are different kinds of anions. So, different kinds of cations include the univalent metals, the multivalent metals, and polyatomic cations. So the univalent metals would be the alkali and the alkaline earth, and silver, zinc, and aluminum. The multivalent metals are pretty much all the transition and post-transition metals except for those three. And the polyatomic cations would be things like ammonium and mercury-1. Okay. Anions, we have the monatomic anions. So this is just, the basic, the nonmetals. And you can get the polyatomic anions. Rather straightforward and simple, somewhat simpler than the cations at any rate. So let's start with the simplest case, univalent metal plus a monoatomic anion. So let's go with calcium and sulfur. Now, you don't actually need to consider the charges for these, because we're talking about just the univalent metals for right now. Okay, so when you do this, of course, be 2 plus, 2 minus, you cross them, then divide by 2, and you get calcium and sulfur, just a 1-to-1 ratio. But for the monoatomic cations, it's just the name of the metal. Okay, the name of the metal is identical to the name of the cation. Okay, so it's just calcium. Now, for the monoatomic anions, you have sulfur. You're going to drop the and add IDE. So you're replacing the ending of it. So it becomes sulfide. Okay, similarly, you could have sodium and oxygen is sodium oxide. And then remember from 9 part 3, you have magnesium. Nitrogen becomes nitride. Okay. So fluorine becomes fluoride. Chlorine becomes chloride. Iodine becomes iodide. Okay, a lot of these are fairly obvious. If they're not, feel free to ask. But let's see, carbon becomes carbide. Okay, so you look at IDE, you're looking at a compound. All right, so now let's cover the case of the multivalent metals. So, multivalent cations. FeO, Fe2O3. Now, oxygen always has a 2- charge, so if this is a 1-to-1 ratio, this is going to have to be 2 plus in order to balance it out. And then for this, you can try reversing it, but you have to be careful because that doesn't always work. But in this case, it does. 3 plus and 2 minus. Those are the two ions you get for iron. Okay, and in order to name a multivalent cation, it's the metal and then a Roman numeral. And the Roman numeral is the charge on the metal. And this whole thing is the name of the ion. Okay, you have to include the charge on the ion and the name of the ion because iron 3 is different from iron, salvage that, iron 2. Okay, so different charge makes it a different species, and you have to indicate what that charge is. So what is this guy? Well, chlorine, let's hop over to the periodic table. You look over here, chlorine is a halogen. It takes a -1 charge. It's only one away from noble gas argon. So that means it has a -1 charge. Multiply by 3, it gets you 3-. Bring that over here. In order to balance it out, you need a total charge. Total positive charge is 3+. Then you divide that by this guy. You divide it by 1. 3+. Okay, in this case, it was fairly obvious. The reason I'm emphasizing the math here is because you can't really do this all the time. You can't reverse cross the streams, okay, because you have to reduce the ratio. So, for example, Ti2C, if you crossed the streams, you would be tempted to think it's titanium 1+ and carbon 2-, but that's wrong, because carbon takes a 4- charge when it goes as an anion. So that means that in order to balance it, 4-, you need a total charge, total positive charge of 4+. So you need to divide by 2, 2+. So that would be titanium 2+, carbon 4-. So over here, it's titanium 3, so this is titanium 3 chloride. And this one here was titanium 2 carbide. So crossing the streams is a great shortcut going from species given to the compound. It is not a good shortcut going from a given compound, like over here with iron 3 oxide, to find out what ions are involved. Okay, so you cannot reverse cross the streams. That only works in one direction. Okay, just like, let's see, to tie it back to algebra, maybe, I don't recall when you taught this rule, but A times B equals B times A. Commutation works, but A divided by B is not equal to B divided by A. We have division involved in this process, so reverse crossing the streams doesn't work. Okay, so that's multivalent cations. You have to include the charge as Roman numerals. So now we look at the polyatomic ions. The polyatomic ions, whether they're cations or anions, are much simpler. Just the name of the ion. So we look at this, we have Na2O2. I'm showing you this because, for the simple reason that, boom, these numbers are not reduced, okay? Which means you're looking at a polyatomic ion. In other words, there are 2 sodium 1+ and 1 peroxide. Okay? So this right here is an indivisible unit. You can't divide that by 2. So be careful with your peroxides. But that is a clue for how you can detect your peroxides. It's the unreduced ratios there. In the same way, you can see Hg2Cl2. Okay. This right here is the positive polyatomic ion, the polyatomic cation, Hg2 2+. And of course, this is chlorine minus. It's just chloride. So naming these two, you just use the name of the polyatomic ion where appropriate. Now, sodium is a univalent or a monovalent metal, so it's just sodium. The ion is identical with the metal there. And then we throw in the name of the polyatomic ion, and that's just peroxide. Similarly, we have to use the name of the polyatomic cation over here, and that polyatomic cation is mercury 1. Okay, so be careful with that one. It looks like, you might expect it to be Hg+, but instead it's Hg2, 2+. That's just the way mercury works. So mercury 1 chloride. I will be including lists of polyatomic ions on your tests, so don't worry about that. But you are still going to have to learn how to recognize them. Just watch out for unreduced ratios is a good clue, but also keep an eye on the charges. Okay, don't just accept that charges work out just fine. For example, it is possible to have something like NaO. See, now NaO2. There we go. It's very, very, very rare, but it is possible. But you should accept that this, a 1+ charge here and a -1/2 doesn't make any sense. Okay, it can happen, but it's super rare. Oxygen hates that. So look out for, if you see something that doesn't make any sense. Here, if you went, with sodium as 1+, and you might assume that this is, then you would go through and find that oxygen is 1-, which you shouldn't ever see. Here, if you started from here, 2- times 2 divided by 2, and so on, you might end up with the result that sodium is 2+, which you should also never expect to see. Okay? So keep an eye on the charges, because if you come up with something super weird, you might have ended up forgetting about a polyatomic ion. Let us do some quick practice examples, going from names to formulas. Yes, names to formulas, and from species to formulas to names. Okay? In other words, you can have the species involved, you can have the ionic formula, and you can have the name of the compound. So for example, let's go with something strange, Sc3+, and NO3 1-. So this one is fairly straightforward in terms of balancing it. You just cross the streams, and that gets you the formula of Sc, invisible number 1, NO3 3. Okay, this right here is a parentheses. You put parentheses around polyatomic ions in order to make multiple, in order to say that there are multiple units of that polyatomic ion in your formula. Okay, you could do similar with ammonium, and let's go ahead with peroxide. You can have 2 polyatomic ions, no problem. You cross, and you get NH4, parentheses, 2, O2. And remember that there's sort of an invisible parentheses around that peroxide and a number 1. So you're not allowed to divide that oxygen. That's why it looks like an unreduced ratio. It's not actually unreduced. It's just that you don't see part of it. Okay, as for names, well, this metal here, we come over to the periodic table. I don't know if you can read it. It's a polyatomic, or not a polyatomic, a multivalent metal. Okay, it's one of the transition metals. So it's right here, it's number 21, it's scandium. The name of that metal is scandium, or sorry, the name of the ion is scandium 3. It can take more than one charge. And then we need the name of this polyatomic ion, and I'll save us from looking it up on a list. It is scandium-3 nitrate. And then down here we have 2 polyatomic ions. This one is ammonium. And this one here is peroxide. Now let's try something a little different. Let's do this. Now, in order to figure this one out, you need to find out the charges on our 2 species. So, coming over to the periodic table, you see iron is right there in the middle of the transition metals. So it's going to take multiple charges. We're going to have to put the Roman numeral on its name. In order to find out what its charge is, we have to look over here at nitrogen. Nitrogen is one of the nonmetals. It takes a negative charge. 1, 2, 3 steps away from neon. So it is nitrogen 3-. So 3- times 1 for a total of 3- gives us a total of 3+ divided by 1 gives us 3+. That's a fairly simple and straightforward example. I like those. So that means that this has a 3+ charge, this has a 3- charge, and the name of our species is iron 3 nitride. Let's keep going. Let's see, mercury 2 phosphide. Notice that's phosphide, not phosphite. Okay, so phosphide means, IDE, we're just looking at the element, not PO3 3-. Okay, that's phosphite with a T, so not this. Yes, this. Okay. IDE means it is just the element. In order to figure out the charge on phosphide, we hop over to the periodic table, and phosphorus is right underneath nitrogen. So 1, 2, 3. So it is 3-. And this is mercury 2, so it is just 2+. So now, from the name, that gave us our species, Hg2+, P3-, and we cross the streams, give us Hg3, P2. Now let's go ahead and go from the name of our compound using a polyatomic ion. So let's try, let's be interesting. Gold 3 carbonite. Okay, so gold 3 is fairly straightforward, a U 3+. And what about carbonite? Well, that is a polyatomic ion. The ITE gives that away. So it's going to have carbon, and it's going to have some number of oxygens. And let's see if we can't figure out what the number of oxygens is and what the charge is. All right, it's not one of the halogens. Okay, those could be anything, 1, 2, 3, or 4, all of them with a -1 charge. So instead, we're looking at this row and this row. Okay? And further left means a higher charge. Further up means a lower charge. Okay? So sulfur is 2-, phosphorus is 3-, nitrogen is 1-, carbon is 2- charge. What about the number of oxygens? Well, that also works because this row is 4 and 3 for atonite. This row is 3 and 2 for 8 and ite. So carbonite is CO2 2-. So now we have our 2 species, CO2 2-, and we can cross the streams. AU2 CO2 3. Don't forget the parentheses. Those are vital. Okay, so that is ionic nomenclature. I will always expect you to be able to go back and forth from the name to the formula to the name. And so long as you're dealing with a univalent compound, alkaline earth, or the staircase. Okay, and if you're dealing with one of these three groups, I will also expect you to be able to go from just the species to the other two. But if you're dealing with a transition or post-transition metal, then you can't you can't do that. You can't go just from the species to the other two things. So I wouldn't expect that. All right. And we've gone on a little bit long, so we'll come back and we'll continue Lecture 10 in the next video.